The coldest place in the universe isn't in empty space. The coldest known place in the universe is not some dark patch between galaxies. It is not a lonely region far from every star. It is a dying star system about 5,000 light-years away, and somehow it made gas colder than the faint afterglow of the Big Bang itself. That sounds backwards. Space already feels like the natural home of cold. It is black, empty, and brutal. So if there is a coldest known place in the cosmos, most people would expect it to be empty vacuum far from everything. Instead, one of the strongest contenders is the Boomerang Nebula, a ghostly cloud created by a star in the last stages of its life. And what makes it so interesting is not just that it is cold, it is how it got there. Because the Boomerang Nebula is a reminder that in space, the strangest extremes often do not come from stillness. They come from violence, motion, and change. The Boomerang Nebula is what astronomers call a preplanetary nebula. Despite the name, it has nothing to do with planets. It is part of a short transition phase in the death of a sun-like star. A star like our Sun spends most of its life fusing hydrogen, but eventually it runs low on fuel, swells into a red giant, and begins shedding its outer layers into space. For a brief stretch in that process, before the exposed core becomes hot enough to make the gas glow like a classic planetary nebula, you get this dim, in-between stage. That is where the Boomerang Nebula lives. So this object is not a birthplace, it is a last act. Hubble first showed a dramatic bow-tie-like structure with two opposing lobes of material blasting out from a hidden central star. But later observations with ALMA revealed that the visible light view was only part of the story. The famous boomerang shape is partly a trick of light. A dusty lane near the center acts almost like a mask, allowing starlight to leak out mainly in two narrow directions. That helps create the familiar hourglass appearance. So even the object's shape is a lesson in cosmic misdirection. But the real shock is the temperature. The universe is filled with a faint thermal glow left over from the early universe, the cosmic microwave background. Today, that background sits at about 2.7 Kelvin, just a few degrees above absolute zero. So truly empty space is not at zero. It sits inside a weak bath of ancient radiation. The Boomerang Nebula managed to drop below that background. Measurements have shown parts of it reaching roughly 1 Kelvin above absolute zero. That is the part that feels almost impossible. How does a star, which we normally associate with heat and light, create one of the coldest known environments in the cosmos? The answer seems to be expansion. When a gas expands very rapidly, it cools. You can see the same basic effect on Earth in compressed gas systems. Release the pressure fast enough, and the gas temperature drops. In the Boomerang Nebula, something much more extreme appears to have happened. The dying central star blasted material outwards so fast that the expanding gas cooled to extraordinary temperatures. Instead of heating the surrounding region into a bright shell right away, this outflow produced an ultra-cold envelope. That overturns instinct. It is a cold object made by a star, not because the star faded quietly, but because it threw matter outwards so violently that the gas chilled as it expanded. And astronomers do not think this was a simple stellar wind. One leading idea is that a smaller companion star plunged into the swollen outer layers of the red giant. If that happened, the interaction could have helped hurl much of the giant's outer material into space. The result would be a fast, dense outflow of gas and dust, exactly the kind of event that could explain both the nebula's shape and its extreme cooling. In other words, the coldest known object in the cosmos may exist because one star effectively fell into another. That is not confirmed in every detail, but it is one of the strongest explanations on the table. The scale makes it even stranger. This is not a tiny frost pocket drifting near a dead star. The outflow stretches across an enormous region. The whole structure reaches lengths comparable to a large fraction of the distance from the Sun to Alpha Centauri. This is cold on a stellar death scale, and that matters because it changes what cold means in astronomy. Usually when people imagine extreme cold in space, they imagine absence. No sunlight, no nearby star, no heat source. The Boomerang Nebula shows a different route to cold. You can get there through dynamics, through matter moving and expanding faster than your intuition expects. That makes the object important beyond its own oddity. It gives astronomers a rare look at a brief and unstable stage in the death of sun-like stars. Preplanetary nebulae do not last long on cosmic timescales. They are faint, transitional, and relatively hard to catch in detail. So every one of them gives scientists a chance to watch stellar death while the geometry is still being written. And the Boomerang Nebula is one of the most dramatic examples because it is not just transitional, it is extreme. There is still a lot scientists do not know. Astronomers are still working out the full history of the system, the exact role of any companion star, and the detailed mechanics of how the outflow reached such severe temperatures. They are also still piecing together how much of the shape we see comes from actual structure, how much comes from dust, and how much depends on the wavelength used to observe it. That uncertainty matters. The Boomerang Nebula is not interesting because it is a neat, solved puzzle. It is interesting because the broad picture is clear while the mechanism is still being refined. A dying star created an ultra-cold outflow. But the full choreography of how that happened is still being reconstructed. And that is the payoff. The coldest known place in the universe is not simply where nothing happens, it is where something happened so violently and so fast that it pushed matter into a state colder than space itself. That is a very different picture of the cosmos. The universe is not only shaped by heat, fusion, and collapse. It is also shaped by expansion, hidden companions, dust, geometry, and brief transitional moments that can produce conditions more extreme than our instincts would ever predict. If you want the next step after this, the natural question is just as strange. When stars like the Sun die, why do so many of them leave behind beautiful, symmetrical nebulae at all, instead of just falling apart into a messy cloud?